Thank you very much. I'm very happy to be here again. Thank you to the organizers for the invitation to speak also. This is a joint work with Yuta Kusakabe that I will speak about, a very recent one. First, it will be about a topic that I talked about often in the past, but maybe not very recently. So I'll just recall what is an Oka manifold. It's a subject which developed over as you will see from the next slide, so over some 70-year period, or actually more now. So okay, here. So a complex manifold, Y, I call it an Oka manifold after Kiyoshi Oka, if maps from any Stein manifold X to Y, or from any reduced Stein space, satisfy what's called the H principle, or the Oka principle in this case. So this means, first of all, if you start with a continuous map, you should be able to deform it to a holomorphic map. But sometimes this condition is trivial because maybe Y has no topology, so you just contract it to a point or something. So in addition, you actually ask that if the given map is already holomorphic on some compact holomorphically convex subset of your Stein manifold, and maybe it's also holomorphic on some closed complex subvariety, then I should be able to choose this homotopy from the beginning map to the final holomorphic map in such a way that all these maps in the family remain holomorphic in the neighborhood of K and actually as close as you like to the original map on K, and on X prime, on the subvariety you want to interpolate. Don't change at all. So this is the requirement. And this requirement makes the situation non-trivial because then you see that, in fact, this will very rarely be true. For most manifolds, it won't be true. And also, then we call this last condition, which I didn't spell out precisely, I call it a parametric Oka property. So basically, it comes in application. It's very important for applications to have parameters. So this means that instead of looking at a single map, you start with a family of maps which depend in addition on a parameter in some compact Hausdorff space, just continuously. But you typically have conditions that for some values of the parameter, maybe your parameter is just the interval 0, 1, and then for the end values, your map is already globally holomorphic, and that's fine, you want to keep it. So such conditions are called parametric Oka property. Okay, so these properties say that in the absence of topological obstructions, you can say that holomorphic maps from Stein manifolds to these Oka manifolds satisfy exactly the same conditions as holomorphic functions on Stein manifolds. Namely, this approximation condition is nothing else but the Oka-Weil approximation theorem if you talk about functions. And the interpolation condition is the Oka-Cartan extension, interpolation theorem or extension theorem. The parametric case has not been considered classically, but as I say, in this theory, it's very important. Now I could say a lot about these, what are properties of these manifolds. So first of all, you see immediately that actually it's not hard to see that you can map Euclidean space. So if Y is Oka, then you can map Euclidean space if X is Cn, with n being the dimension of Y. You can map it on surjectively so that it's actually strongly dominating. So this means every point in the image is hit by at least one point where the map is submersive. So in some sense, Oka manifolds are images of Euclidean spaces, dominated strongly by Euclidean spaces. But that's but much more. Also, you notice right away that they cannot admit any bounded plus superharmonic functions. So they are Liouville manifolds and so on and so on. So here I'm listing my paper from 2009, where this class was first introduced formally. And why? It's because that year I proved, I will show you later, I proved that in fact, several of these conditions, if you take them individually, are actually pairwise equivalent, and I found a simple characterization. So I thought it was a good time, 2009, 70 years after the first paper of Oka in this direction, to call them Oka manifolds. And then a bit later, they entered into the classification of mathematical subjects. So here is just a very brief history, only the key things which happened. So Oka in 39, this was one of his first papers. He showed that the holomorphic classification of line bundles on the domain of holomorphic coincide with the topological classifications. In modern language, you could say that he really showed that C star is an Oka manifold. Of course, Euclidean spaces are, but and then the next major development is due to Grauert, who showed that every complex Lie group and complex homogeneous manifold, these are all Oka manifolds. Of course, he didn't use this language, but he proved the conditions, which I showed you on the previous slide. And his application was, in fact, that when he generalized the statement of Oka to the case where you look at principal G bundles, where G is a Lie group, complex Lie group. So the classifications coincide in the topological and holomorphic category. And then there was a development by the German school, but I won't talk about that since I don't have the time. More or less, it went up to the early 70s, and then there was a 20-year gap when essentially nothing happened until Gromov came around, and of course, he was interested in a few years later, he published his book in which he developed the H principle to somehow very modern level, so-called homotopy principle. And then for him, this was very natural because it's a kind of homotopy principle in the holomorphic setting for complex manifolds. So he gave several sufficient conditions for a manifold to be Oka. In particular, he introduced a condition that he called ellipticity. In fact, he introduced several ellipticity conditions, but I'll show you what this condition is on the next slide, so I won't say now. So he introduced a class of manifolds that he called elliptic, and they're all Oka. In particular, if you have a manifold, this second condition is easier to imagine. If you have a manifold which admits many complete, C-complete holomorphic vector fields, by many, I mean that they span point-wise the tangent space at every point. Such manifold is now called flexible. This condition was introduced more recently by Argent and several other authors. Okay, so we have many of these vector fields. So this means their flows are actually one parameter subgroups of the automorphism group of your manifold. Then Y is elliptic in the sense of Gromov and hence Oka. So there were sufficient conditions. And then, and actually it wasn't understood if you look at these properties which are listed here. At that time, it wasn't understood whether these properties, if you take them individually, you just take the approximation property, say, or you take the interpolation property, and you take without parameters or with parameters. So there were many Oka properties floating around. But then I introduced this axiom in 2006. This axiom, which I call convex approximation property. So it's a simplest, I ask, so the axiom asks that every holomorphic map from a neighborhood of some compact convex set, actually from an arbitrary compact convex set in any Euclidean space, should be approximable by entire maps into the manifold. It's an Oka type condition, but the good point here is that the source is extremely simple, convex, contractible, no topology. And using this condition, first I show that this implies all of the Oka properties which you saw in the previous slide, and also all these properties are equivalent. There was a 3-year gap between the first and the last paper. In that last paper, then I introduced the class of Oka manifolds, when also the parametric case was understood. Okay, so this is the definition of what it is. And then after 2009, well, there were some developments. We found new examples. But actually, I have to say that for that decade, we were lacking examples. We had some which we knew before, and we didn't develop very many new, because it turns out that this cap condition, it did prove certain, it was a good condition to kind of establish the general theory, to have it well understood. But it wasn't too useful to obtain new examples. Until a young man who was at that time, when he started working, master student of our friend Takeo Ozawa, and then later studied our PhD in Osaka. he started working on the subject, and he made a revolution in the subject. So I'm going to tell you some of the new things which happened since then, and now we have many new techniques to work. So the subject has been really revived. So Utah, first of all, proved the following. This is a characterization which was also proposed by Gromov, but Gromov really didn't do anything about it. I mean, just it was present, this condition L1 was present in his paper. So this condition says, this characterization says the following, that the complex manifold is OCA if and only if for every holomorphic map from, again, a neighborhood of a compact convex set in a Euclidean space, you can find another holomorphic map from the product of this set K with some Euclidean space of high dimension, high at least n, at least a dimension of y, such that at the zero value of the parameter, you have your original map. And then if you differentiate this, what we call a spray map in the parameter direction, so you map Cn to the tangent space, and this map should be surjective for every point for every base point. So basically every map, you can build this tower on it, this tower which you call spray, map from the product of the base cross some Euclidean space. And as I say, this is a restricted version of condition L1, which was studied by Gromov already. He mentions it in his book, and then later in his main paper on the subject. And Kusakabe proved that this condition implies cap. Cap was the property which I showed you on the previous page, which I introduced. And this proof is not difficult at all. It's like 2 pages, but it's a kind of ingenious. I would have never thought of it, and I actually, in all my studies on the subject, I kind of ignored this condition, I have to say. But he showed this implication, and therefore all the rest was known before. And this characterization, as I say, opens the way to new developments. As an immediate application, almost immediate, he showed in the same paper the following theorem, which we like to call localization theorem for OCA manifolds. And this says that if you have a complex manifold, which you can cover by Zariski open OCA domains, this means you have closed complex subvarieties, and this complement is then called Zariski open, not in the algebraic sense, but in the holomorphic sense. I mean Zariski. And if you can cover Y, if Y is a union of such things, and each of them is OCA, then Y itself is OCA. And this somehow, how would this go? Well, actually use this characterization here. The idea is simply that you have a subvariety, and you have a map inside from your K. Okay, maybe I draw a picture. Let's say that here is a subvariety A. This is the manifold Y. And let's assume that this domain is OCA. Let's say I know this. And now some holomorphic map comes in. So the image intersects. So this is f of K. And actually, I already proved some 10 years before that if you know that this complement is OCA, then what you can do, you can build a spray on this F, which is not dominating everywhere, because here on A, I don't know anything. I don't know how to move it. But here it will be degenerate, but elsewhere it will be dominating. So I can build something, I can make it thick everywhere except on K. I can build a kind of partially dominating spray. It's dominating at each point which doesn't go to A. And then I continue. Then I take this as my new base map, and I take another subvariety, and again I add to it some dimensions and extend. So after finitely many steps, I can actually get domination. He can get domination. Okay. And then Utah moved forward, and in 2020 wrote a beautiful paper, which just a month ago was accepted for publication in the Annals. And in this paper, he had many new examples, and these examples were of the following type. The basic one is if you take a compact polynomially convex set in a Euclidean space of dimension more than 1, then he showed that the complement of this set is an OCA domain. This was a long time open question, even for the case when K is the ball. The same is true with the same proof, essentially, if you replace Euclidean space by one of the Stein manifolds having Varrolin's density property. I will define this later. This density property means, again, that there are lots of complete holomorphic vector fields on the manifold. Maybe I'll give you an idea of this, how you see that. Yeah, let me give you an idea. We have known long before, so let's say here is Cn, and you have some compact polynomially convex set. It has been known since long time before that you take a point outside, then you can find the 2 Bieberbach domain. So it's an image of a holomorphic map from Cn, actually biholomorphic map from Cn, so that 0 goes to this point, and the image of F does not meet K. Okay, that has been known before, and how would you do that? Act 1 construction is the following, that at this point you create a vector field which is contracting here. Just take a simple contraction by a factor of one half, for example, to that point. So that vector field you will consider here in the neighborhood of this point. So you take vector field V, holomorphic, which is contraction there, and here on the neighborhood of K, you take V to be 0. And now what you do? Well, now K union a little ball around that point is, of course, still polynomially convex, so I can approximate this vector field by global vector fields. But now comes the Anderson-Lampert theory in the picture. Anderson-Lampert theory says that each holomorphic vector field on Cn can be approximated on compacts by sums of complete holomorphic vector fields, actually by sums and commutators, by Lie algebra of complete vector fields. And based on that, we have it was a year after a paper by Anderson and Lampert was published on that subject, Jean-Pierre Rosé and I had a paper in which we showed that actually that from their work you can deduce that anytime you have such a flow, you have a one parameter isotopy of biholomorphic maps between domains in Cn. So you start with the domain, you start with identity, and then you move it. Okay, each map is holomorphic. And let's assume that each domain in the process is Runge in Cn. Then the conclusion is that the whole homotopy can be approximated by isotopy of automorphisms. So in other words, you look at this flow here, which is contracting, and here you are doing really nothing. You're almost not moving. So you can find an automorphism which does almost this. Now you repeat. You keep repeating. So you iterate, but not the same automorphism. Each time you take a new one because you have to approximate more and more. Here you have an attracting basin, what is called a random basin, and that's a Fatou-Bieberbach domain. Here you ensure that each time you approximate better so that no point from here can go there. That is the proof. Well, it turns out that if you look at this proof, you can also prove the version of this theorem when this point starts varying. That means instead of a single point, you now take a holomorphic map from some set K, I mean not K, not this K, some other convex set into here. So the point moves holomorphically depending on some other variable. And then you can make this construction in such a way that these Fatou-Bieberbach domains which you get also vary holomorphically, and they always stay in the complement of K. And you see that creates a spray of this kind. Because I take F as being this map which maps 0 to this point and maps Cn to this Fatou-Bieberbach domain, and then actually no, F is just a map which maps some convex set, like in this definition, I have a problem because maybe I should take this to be L, and then it will be fine. Okay. So K is somewhere else. So now you map K in here. So each point will go to some point there, and then you apply this thing. And what is your capital F then? Capital F is precisely the map which is in the second variable. It's a Fatou-Bieberbach map in the second variable, and the center of this Fatou-Bieberbach map, where you take the point to be 0, is just your point F, where you want to be. So it's like a holomorphically varying family. So this gives exactly a spray of that kind, even a very special kind. Okay. Why there is a problem here, because I don't see where is now that slide I was talking about. I think I maybe skipped the slide before, didn't I? This slide I have accidentally, I'm very sorry, I have skipped the slide, but since I skipped it, let me continue with this slide and then return just for some definitions to the previous one. So Utah, with a similar technique, also showed that the following is true, and this is now a kind of important generalization of the previous theorem. So now you take again a closed, possibly unbounded, polynomially convex subset of Cn. What do I mean by polynomially convex when it's just unbounded? Well, I mean that it's exhausted by an increasing sequence of compact polynomially convex sets. Okay, and I assume that it's contained in such a domain. So I have here, I split Cn into this product. And the second variable should be less or equal than some positive constant times 1 plus the first variable. So it's a kind of conical region in which this lies. Then it turns out that the complement is again an Oka manifold, with a little bit of similar proof, but using his characterization. And here is a further generalization. But I should maybe, I'm talking of the Oka property of a map, and this was done in the previous slide. So let me return to the previous slide. Not only we have Oka manifolds, but we have Oka maps. What are Oka maps? You consider a diagram like this. So here, this X will be always Stein. This vertical map will be just some holomorphic map. Typically, it will be a subversion, but then we consider holomorphic maps this way, this little f from X to B, and we would like to lift them to holomorphic maps. And actually, the Oka property says that, I mean, this map P from E to B satisfies the Oka property if the following is true, that any time when this bottom holomorphic map admits a continuous lifting, then you can change that continuous lifting homotopically through liftings to a holomorphic lifting. And again, you ask for the similar approximation interpolation properties. So this is called the Oka property of the map. I have shown some time ago that for holomorphic submersion, this property is local on the base. This means the property holds if every point in B has a neighborhood so that the restricted submersion has that property. And then one more definition, a holomorphic map is called an Oka map if it satisfies this property that I said before, and in addition, it's a topological fibration. Topological fibration just refers to the possibility of the homotopy lifting property. You have a homotopy downstairs, you lift it at the initial stage, then you should be able topologically to lift it. It's a fibration. So here what we need to know for the rest of the talk is this theorem that a holomorphic fiber bundle with an Oka fiber is an Oka map. And even more importantly is this in blue. If you have an Oka map, for example, a fiber bundle with an Oka fiber, in particular a covering map, then the bottom and the top manifold are Oka at the same time. One is Oka if and only if the other one is Oka. So Laruson actually developed a nice abstract homotopy theoretic interpretation of this subject in which Oka maps are what is called fibrant, and and Stein inclusions are cofibrant, and so on. And again, from Kusakabe's recent work, we have a very important new tool which says that if you have a complex manifold which admits sufficiently many holomorphic maps to some other manifolds so that these maps have the Oka property. What I mean by sufficiently many, I want that the kernels of the differentials of these maps at every point of y span the tangent space. So this means I have some kind of projection, right? It's a good projection, an Oka projection. Then I look at the kernel. If there is no kernel, then you do it with one step. But if there is a kernel, well, then you want to use projection in a different direction, and you want that these kernels add up to the span the tangent space. Then y is an Oka manifold. And this is also not hard to see, because you see, what is the point? The point is that each time you have an Oka, such a projection, then you can verify this condition of Kusakabe, that you have to build a dominating spray. You can make a spray which is partially dominating, namely, it is dominating in the direction of the kernel of this differential, in the vertical direction, sort of. So if you have now, okay, you take such a spray, then you have another projection slanted in a different direction. You again use that and build on top of the first spray, you build the second spray. And in finitely many steps, you find a spray which is dominating in all directions. Good. Okay, so these three things we'll use. Then I also want to mention that from Kusakabe's results, last year I talked about some joint results of Erland Wold and myself. We proved, for example, that for most closed, unbounded convex sets, the complement of such a set is Oka. So this again, I find interesting because this means, why do I find this interesting? It's because, so here you have Cn. Let's say that this is a hyperplane, real hyperplane. Well, in this picture, the bottom and the top, so this, both domains are Cn minus 1 cross a half plane, cross a disk, you can say. So this is a disk. And the same here. So this means that neither half is either hyperbolic, because there is this factor, neither Oka, because there is this hyperbolic factor. Oka manifold cannot have any hyperbolic factor in it. Now, if I make this H just slightly convex, tilt it up a bit, take a convex graph over it, then what turns out is that what is below is Oka, and what is above is hyperbolic, Kobayashi hyperbolic. I have very many splittings of Euclidean space in the Oka and hyperbolic part. So this is, of course, convex is only a special case. Actually, a more general version of this theorem is that if you take an unbounded closed set in Euclidean space, which has the property that there is some complex hyperplane which avoids it, and such that the closure of these two sets of the domain and the hyperplane in the projective space. So you compactify Cn with a projective space. You ask that the closure of the hyperplane and the domain and the set K don't meet also at infinity. They don't meet either in Cn or at infinity. Yes. And then you ask, so I have a, let me draw this. So imagine that this is now a complex hyperplane. So here is some domain, okay, which is possibly unbounded. And I'm compactifying everything in the projective space. So this is hyperplane at infinity. This here is Cn. And so now I'm asking that K, the closure of K is equal to its polynomial hull in where? Not in this Cn, but in the other affine chart, which you get by taking Cpn minus lambda. And this is again Cn, just another affine chart on Cn. So if the closure of K in projective space, of course it should meet lambda, as I wrote, and then it should be polynomially convex, then the conclusion is that Cn minus K is Oka. So we have many such examples with unbounded things. Okay, but let's go on. And now I come actually to what I wanted to talk about. And here the question is the following. I was a little bit motivated with this question, with this work that we did with Erland. And the question is the following now. I look at a holomorphic vector bundle on a connected compact complex manifold with a Hermitian metric. And the question is, I will mostly look at line bundles. So I look at this disk bundle. This means the set of points where the norm is less than 1. And I want to know, when is this an Oka manifold? In particular, I'd like to know, when does the 0 section admit a basis of open Oka neighborhoods? And can we say something about vector bundles of higher rank? But we shall mainly focus on line bundles. Okay, so this is what I'm interested in. Can we have Oka disk bundles in line bundles? Now let's look at immediate observations. First of all, it's immediate from the previous theory that the total space of the bundle is Oka, if and only if the base is Oka. This is because the fiber is C, which is Oka. It's also obvious that these disk bundles are biholomorphic to each other by dilation in the fibers if you change the radius. So the second question has affirmative answer if the first question has the affirmative answer. Another thing which we notice immediately is that if that this disk bundle can, of course, holomorphically retracts just by the projection down to X. And it's now that easily observed that if this disk bundle is Oka, then the base should be Oka. So we should only look at the Oka basis. And another immediate observation is that this never is true on a trivial bundle. On any trivial bundle, this is false. Why? Well, because in such case, X is compact. The disk bundle or the ball bundle will be contained in the product of X with some ball. And the ball is hyperbolic. And so you have a non-constant, you have a fluid superharmonic functions here, which are non-constant at each point. And so the same is true on the product. And therefore, this cannot contain any Oka domains. So these are immediate observations. The finer observation will depend on the curvature, naturally. So let me just recall briefly something about line bundles, which you all know, but anyhow, I'll just go quickly. So we recall that the Picard group measures the holomorphic isomorphism classes of line bundles. We have a natural homomorphism onto the H second cohomology group. In the case of, I shall now look at projective spaces as a model Oka manifolds. These are complex homogeneous, therefore Oka. So the Picard group on CPN is well known to be Z integers. We write the line bundle corresponding to integer K as follows, as OCPNK, with this bundle corresponding to 1 being the hyperplane section bundle and the -1 being the universal bundle. And OCPNK is just the kth tensor power of the hyperplane section bundle. And I call them either positive or negative depending on what is K. Okay, now, so every such bundle on every X is defined by a transition cocycle. And if you fix such a transition cocycle, then a Hermitian metric will be given on any line bundle chart by in this way, right? It's a fiber variable T absolute square times some positive function in front, and these functions have to satisfy this compatibility condition on the intersections. If you take tensor power of a line bundle, then all the functions here, the ph's and the h's, will be raised to power k. Okay. Now, this is the important notion. We say the bundle is curved positively or negatively if this real one form, I times theta, which really comes out to minus a half of DDC of logarithm h, if this is positive or negative. Or we also call it semi-positive if it's bigger or equal to 0. So from this is well known. And from this, you see that you have a correspondence between positive or semi-positive metrics and functions h, whose logarithm, whose minus logarithm is plurisupermonic. So you have a minus sign there, so that's why you have the opposite. So in particular, this means that if you have a semi-positive metric, this is equivalent to saying that the disk bundle is pseudo-concave along the hypersurface. Okay, and vice versa. Semi-negative means the disk bundle would be pseudo-convex. And here is our first theorem. This is not our main theorem, but this theorem is a little bit easier to explain. It was the first thing which we had. So let me explain this one. So this theorem says that in a line bundle, you take a line bundle, one of these CP, O, CP, and K, where N is at least 1 and K is at least 1. You take a positive one endowed with a semi-positive Hermitian metric. The following assertions are true. First of all, the puncture disk bundle, this means I remove the 0 section from the disk bundle. This is OCA, always, and the disk bundle itself is OCA1. I didn't introduce this condition, but OCA1 essentially means the same thing as OCA, except that I'm not using all Stein manifolds as sources, but only open Riemann surfaces, holomorphic curves. So OCA1 manifold, which was only introduced this year, means it's a manifold with an abundance of open holomorphic curves. The main statement is actually the second one. That's why I made it blue. If n is at least 2, the dimension of the base is at least 2, or if E is the hyperplane section bundle in any dimension, then the disk bundle is an OCA manifold. And the complementary tube, which means the exterior tube where the norm is bigger than 1, that is Kobayashi hyperbolic. So again, you see, you have a splitting in a semi-positive bundle. You have a splitting. The tube is, of course, relatively compact, and it's OCA, and what is outside is hyperbolic. It's a little bit similar to the splitting we had in the Euclidean space. What about if the bundle is semi-negative? So this means K is less or equal than -1. You have a semi-negative metric on it. Then it's just the opposite. The inner and the outer, the role of the inner tube and the outer tube get switched. So in this case, the punctured disk bundle is Kobayashi hyperbolic, and the outer tube is OCA. And this second part is actually a direct consequence of the first part, as I will show you in a later slide. Why? It's because that's what happens when you invert the bundle. When you have a line bundle and you take its inverse, then even if you have Hermitian metric, you take its Hermitian dual, then what happens is that the inner tube, punctured inner tube, gets mapped to the outer, is the outer tube for the dual bundle, and vice versa. So these second statements are there really just a consequence of the first three. And I also want to point out that these results don't require the metric to be smooth, even though I use DDC and so forth. But actually, if H is continuous metric and semi-positive in the weak sense, that's enough. That's enough. And also, it's true that the restrictions of all these bundles, any affine Euclidean chart, have the same property. So for example, if you take the second statement here, and you, instead of E, you restrict to this E to an affine chart, it will still be true, what's written. Okay, let me show you a little bit why is this true. So in fact, for the hyperplane section bundle, this is a mere observation, and this led me to this theorem originally. Because what is the hyperplane section bundle? What is the total space of it? Right? It's very easy. It's essentially like in this picture. Okay, so imagine that in this picture now, my base is this one. This is CPN. And I'll think of it as a hyperplane at infinity. And this inside here is 0. This is now Euclidean space of dimension CPN minus 1. And you can identify E, the total space of E, which is O CPN plus 1, with CPN plus 1. The total thing is now CPN plus 1, right? CM plus 1 union H. Okay, so you can identify it with this minus 0. Actually, 0 is arbitrary. You can take any point in the projective space, and the complement is a hyperplane section bundle. But this is the 0 section. These lines which go through are, well, the fibers of the projection, but you puncture them here. You remove 0, but you add this point at infinity. So this is the picture. This is the total space. It's well known. So what is the neighborhood? Okay, so this thing is a 0 section. And then you look at what's written there. So you have a semi-positive Hermitian metric. Then you look at the disk bundle. This is a pseudo-concave domain containing a thing at infinity. And its complement, K, which is where H is big or equal to 1, is a compact set in here, which is sliced by disks because you have a Hermitian metric. And this set is polynomially convex. Why? First of all, it's defined in this way as 1 over H less or equal to 0, less or equal to 1. But you see 1 over H is e to minus log H. And this one is plurisupermonic because minus log H is plurisupermonic. So this set is defined by a sublevel set of a plurisupermonic function, so it's polynomially convex. But then I can use two theorems which I mentioned before. One is maybe this one. What is the deleted disk bundle? It is simply Cm plus 1 minus K. So it's everything outside K is the deleted, is the punctured disk bundle at infinity. And if I take the complement in CPM plus 1 minus K, this is the disk bundle. And this one is also Oka. I think I showed it in a previous slide, but I didn't explicitly point out. Okay, so this is really an observation, simple. However, I don't know a comparably simple proof for other bundles. And now I'll give you an idea how you do it for the other bundles. First of all, I need the following information. I look at very specific Hermitian metrics on these bundles. Namely, here is the formula. Here is the formula. So Zi, these are coordinates. Z capital I are the affine coordinates on the ith chart. These are transition functions on this bundle. And so you see that H defined in this way is a Hermitian metric. It matches this transition functions correctly. The curvature of these specific forms of these metrics is just K times the Fubini-Studi form. So when K is equal to 1, this is positive. And the disk bundle grows at this rate because the disk bundle is where H is less than 1. So you see from this formula that in a chart, it grows like this. So let me draw a picture here. No. So what is important here is that if K is non-negative, then these domains are Hartogs domains whose radius, if K is positive, it grows. If K is negative, then it decays. at infinity. But I'm looking at the case where k is positive. So the bundle looks like this in the chart. So this is my, this is the disk bundle restricted to this chart. Let's call this domain omega. It's a Hartog's domain, which, whose radius grows at least linearly. In this case, bigger or equal to 1. And now the point is, if I denote by S the complementary set, this is Cn, but there is a vertical axis here, right? C, I mean Cn plus 1 minus omega bar. Let's denote by S the set. Let's continue. The lemma says that such a domain, which I drew here, so it's a pseudo-concave Hartog's domain, which grows at least linearly at infinity, that such a thing is Oka. So if I know this, then I have really proved the theorem. Why? Because you see, this bundle is covered by such Zariski open domains for affine charts covering CPN. So it follows that if I know that each of these is Oka, then this guy is covered by Zariski open Oka chart. So it's Oka by localization theorem. Okay, so I have to know that this is Oka. But this now is not too difficult because I look at, here I can now use, we can use Kusakabe's theorem. We look at this projection. I call this variable t, and the variable here is called z. So the total variables are z and t, and I look at capital T is a projection on the t factor. And because I have this linear growth, I see that this projection T, I see that, so S is the complementary domain, and it's defined as follows, where T is bigger or equal to phi. Phi is now plurisupermonic, so actually even logarithm phi is plurisupermonic. This function minus logarithm of T is harmonic where T is non-zero. So this on the left side is a plurisupermonic function, which I call psi now. This is plurisupermonic. So again, S is defined as a sublevel set of a plurisupermonic function. However, notice that this function goes to infinity where T equals to 0. So it's actually plurisupermonic on this product, Cn cross C star. So I have to exclude this axis. I have to exclude. So this set S, from the next line, you see that this set is holomorphically convex inside Cn cross C star, because it's actually, if you cut it off at the level R in the T direction, then this becomes defined by two plurisupermonic functions, namely this and that. And therefore, this set is holomorphically convex, so the union S is holomorphically convex. But now I can use Kusakabe's theorem. Kusakabe's theorem, which I showed you before, precisely shows that this projection, first of all, if I restrict T to S, it's proper because S grows, at least linearly. So the fibers of this projection are compact, right? They're like this. And Kusakabe's theorem says that this projection has the Oka property. That's not enough to conclude that its complement is Oka, but it would be enough if this were a topological fibration, but it is not. You see, topology changes. However, I can now do projection in a slanted direction. So I won't go through the slide too much, but I'll just explain what I do. Instead of this hyperplane, I tilt it. If I tilt it not much, it will still not intersect S, and the projection in the tilted direction will still be good. And I can do the argument which I did in front now, I can do for the tilted projection. As soon as I have two tilted projections, then their kernels span the tangent space at every point, and I can conclude that omega is Oka. Okay, so that proves this theorem. In this slide, now I'm kind of over time, so in this slide I explain how, I'll skip all that. And here I explain about the dual bundle, but so forth and so forth. But let me now show you the most general theorem which we have at this point. This is still a developing subject, but the most general theorem which we have based on this idea of proof, which I just showed you, is the following. Now it's stated in a coordinate-free way or ambient-free way. I have a compact complex manifold X as a base. I have a semi-positive Hermitian holomorphic bundle on it. And I assume, this is the key assumption, that for each point, there is a divisor in the complete linear system given by this line bundle. So what this means? This means that there is a section, holomorphic section of E, which has D as the zero locus. Okay? So I have such a divisor whose complement is a Stein neighborhood of X, which has the density property. This density property again means what I said before, that you have a lot of complete holomorphic vector fields on it. So you have this approximation theorem of Anderson-Lempert type. Then the disk bundle is an Oka manifold, and the complementary thing is again hyperbolic domain. And here is a brief idea of proof. Essentially, we use this, using this assumption here, it's easy to see that there is a holomorphic map, Kodaira type map from X to some projective space, which, so for each such, if I fix a divisor, it suffices to show that this is Oka, and the bundle on the complement of the divisor is of course trivial, because that's by definition, because that's where the section which I have is non-zero. Since the complete linear system is base point free, this means this intersection of these divisors is empty. There is such a map to projective space and a hyperplane in the projective space, so that E is actually the pullback of the hyperplane section bundle, and the inverse image of the complement of the hyperplane is exactly the complement of this divisor. So this shows that, in fact, this pseudo-convex Hartog's domain, just like in this picture, grows at least linearly, because I know what happens here. I have hyperplane section bundle, and I simply pull it back. And more or less, we do the same proof as before, except that the base manifold is now not Cn, but it is this X minus D. But X minus D is good because it's a Stein manifold with a density property for which the previous method works. Okay, I skip this too. I only want to show you an open question, which might be of some interesting. One might ask, what happens when you have a vector bundle of higher rank? Is the tube still Oka? So in that case, the tube, the fibers are strongly pseudo-convex domains, right? Which grow well, but the problem is that there is something that the Levy form of the boundary is positive in this tangential directions to the fibers, and it's negative in the other direction. So it's a case of mixed signature. Actually, it's a problem in that there is no example in the literature. We don't know a single example of an Oka domain in some bigger complex manifold with smooth boundary, with at least somewhat smooth boundary, which would have a boundary point that is not pseudo-concave, like mixed signature. It's easy to see that strongly pseudo-convex boundary point is impossible, because there you can construct bounded Lewis superharmonic peak function and extend it to zero elsewhere. So that's impossible. But mixed signature, like 1, 1 in dimension 3, we don't know. We don't know anything about that. And this we call the inverse Levy problem for Oka manifolds. Namely, is every Oka domain with smooth boundary pseudo-concave? There is another thing I wanted to point out, since many of you are experts on the, or know a lot on complex differential geometry. It turns out, this is now a heuristic principle that I'd like to formulate. It turns out that the Oka properties of compact complex manifolds seem to be related to metric positivity. I mean, even what I told you today, the important feature of the bundle was to be positive. And that meant pseudo-concave. Here are some examples. It's an old theorem which was started by Mori, Siu, and Yao, and then Mok had the best theorem. And the theorem says that if you look at compact Kähler manifold with semi-positive holomorphic bisectional curvature, they have a classification. They know exactly what such a manifold is. It's a product of some copies of Euclidean spaces, some copies of projective spaces, and some copies of compact symmetric manifold, compact Hermitian symmetric manifolds. And all such are Oka. So I conclude that if you have bisectional curvature, semi-positive, they're all Oka. More recently, Ustinovsky proved a similar theorem for Hermitian manifolds, not necessarily Kähler, but holomorphic bisectional curvature, semi-positive everywhere and positive at a point. Again, it's a projective space and hence Oka. In a different direction, Yang proved recently that a compact Kähler manifold with positive holomorphic sectional curvature now, not bisectional, but just sectional. Such a thing is rationally connected and projective. And in a paper from this year, Alarcon and I proved that every rationally connected projective manifold is Oka1. This means it has an abundance of holomorphic curves. So again, it's a theorem of the same sort. And also this last statement, we don't know whether every compact rationally connected projective manifold is Oka1 or Oka. I mean, we know that it's Oka1. We don't know whether it's Oka. Most likely it's not. But if it were, then by this further result of Matsumura, it would turn out that every projective manifold with semi-positive holomorphic sectional curvature is Oka. But I think that this last thing is likely false. Anyway, I'll stop here and thank you very much.